everyone. I'm going to talk about inferential statistics and hypothesis testing today. Before I talk about what is inferential statistics, I would like you to look at the research example I have here. So the research scenario in this example goes like this. A researcher is interested in the difference between the average math scores of fifth graders taught with traditional teaching method and those taught with game-based method. I hope you can still remember when we talked about descriptive statistics, we mentioned that we want to use descriptive statistics because we want to describe or summarize our data. We will use some indices to describe and summarize our data. If those indices are calculated from the whole population, we call those indices parameters. If those indices are calculated from our example, we will call those indices statistics. We also mentioned that when we use descriptive statistics, we only want to describe our data, and we don't want to do anything beyond that. It's different. When we're talking about inferential statistics, that means we are interested in knowing or we wanted to investigate a relationship. If you look at this research example, you can see the relationship this researcher is interested in is the difference between fifth graders taught with traditional teaching method and those taught with game-based method in terms of their average math scores. It's very obvious for you to see there are two populations. Population 1, fifth graders taught with traditional method. Population 2, fifth graders taught with game-based method. And we know the researcher is interested in the relationship between these two populations in terms of their average math scores. Now here's the question. How can the researcher investigate or examine this relationship? Can this researcher reach out to everyone in population 1 and reach out everyone in population 2 and then give them a math test and collect math scores from both populations and then calculate the average math scores and compare? The answer is very unlikely. It's not really likely for the researcher to do that. Then if it's not really possible for the researcher to do that, what can the researcher do? And then the answer is, of course, the researcher can select example from population 1 and select example from population 2. So here is example 1, a class of 35th graders taught with traditional method and a class of another 35th graders, but they are taught with game-based method. It will be easy to give a math test to these 35th graders in example 1 and also give the same test to these 35th graders in example 2 and collect the math test scores from example 1 and example 2 and then calculate average score, math score for example 1 and calculate the average math score for example 2. Now the researcher wanted to use the average math score calculated from example 1 and the average math score calculated from example 2. Use these two average math scores to draw a conclusion about the average math scores for population 1 and for population 2. In other words, the researcher is using what is known from example 1 and from example 2 to draw a conclusion or to make inferences about what is unknown about population 1 and population 2. If we use some of those terminologies we talked about in descriptive statistics, we know that the average math scores for example 1 and example 2 can also be called statistics because these average math scores are calculated from the examples. And we also know that the average math scores for population 1 and for population 2 can be called parameters because they are calculated or they are characteristics for populations. So we can also say what the researcher is actually doing is using statistics known from example 1 and example 2 to draw a conclusion or to make inferences about unknown population parameters. If you understand what this research is doing, it will be easy for you to understand what is inferential statistics. Let me go to my next slide. As I put it here, inferential statistic is used when you make inferences about a population based on data collected from a sample. As a summary, I would like to do a review about the differences between population and sample. First of all, population is rarely accessible, meaning it's really hard for us to reach out to the whole population in our study. But sample is more readily available. You can select a subgroup from a population as your sample, and you can collect data from your sample. And then you can calculate statistics based on the data you calculated. And then one thing I want to point out here is the reason we are using inferential statistics is we are interested in population. We are not interested in the sample. It's easy to understand. If you are only interested in the sample, you can simply collect data from your sample and to do some simple math calculation, period. That's the end of the story. You don't need any inferential statistics. You need inferential statistics only because you are interested in population. But unfortunately, you don't know about the population. You can only use what you get from your sample. Or in other words, you can only use the data you collected from your sample to make inferences about your population. So population is unknown. It has unknown parameters. So if these parameters are unknown, we can only have hypotheses about these parameters. But example is different. You can collect data from them and then you can calculate statistics from them. And using these known statistics from data to make inferences about those unknown parameters. And then here comes the question. How can you make inferences about population based on the data you collected from your sample? And the answer is we will do hypothesis testing. To talk about hypothesis testing, we first of all we need to know what are hypotheses. As I just mentioned, population is unknown, but we are interested in population. But population is unknown, but we can have hypotheses about population parameters. So hypothesis is about population parameters. This is important. Again, hypothesis is not about sample. Hypothesis is about population parameters. So it will go like this. You have hypothesis about your population or your population parameter to be exact. And then you will use whatever you collected from your sample to test the hypothesis. After you do hypothesis testing, and then you can draw a conclusion or make inferences about population. So this is a general picture or broad picture about hypothesis testing. Of course, if you look at a little bit more in detail about what is a hypothesis, as I put it here, a hypothesis reflects your general research question. And it always involves an interest in certain relationship. For example, like the differences or the effects. And then the first example I put it here is the one I used earlier today. It's about the differences between the average math scores of fifth graders taught with traditional teaching methods and those taught with the game-based method. And the second example is the difference between families of different socioeconomic status in the amount of assistance offered to their children in educational activities. Again, this is hypothesis. Hypothesis is about population parameters. Now let's talk about what is hypothesis testing. We have talked about what is a hypothesis when also we talked about the differences between sample and population. So I believe it will be easy for you to understand what I put it here. So what is hypothesis testing? So hypothesis testing is a formal procedure for testing a hypothesis using data collected from a sample from the population. So the result of hypothesis testing shows how well the data and the hypothesis agree. What does this mean? So it means if the result of your hypothesis testing shows that the data and your hypothesis agree well, that means your data support your hypothesis and you can say your hypothesis is true. But on the other hand, if your data collected from your sample do not agree well with your hypothesis, this is the indication that your hypothesis is not true. Now we know the definition for hypothesis testing. Let's take a look at the specific steps for hypothesis testing. For hypothesis testing, we have 4 steps. Step 1, state hypothesis. Step 2, set alpha level. Step 3, hypothesis testing. And then step 4, make a decision. For now, let's skip step 2. If we skip step 2, the logic for hypothesis testing is pretty clear. You state your hypothesis and you do hypothesis testing, and then based on your hypothesis testing, you make a decision about your hypothesis. Now let's first take a look at the first step, state hypothesis. When stating your hypothesis, you first need to state your null hypothesis. What is null hypothesis? Null hypothesis is a statement of no something. What this something is really depends on your specific research situation. It can be no relationship or no difference, etc. Let me use the research example I used earlier today about the 5th graders. So it's very possible when you state your null hypothesis for that research example, your null hypothesis might go like this. There is no difference between the average math score of the 2 classes of 5th graders that is class with traditional taught with traditional methods and class with game-based method. And then, as I indicated here, this statement about null hypothesis is so wrong. Can anyone tell me why this is wrong by having a null hypothesis like this? I hope you can still recall. I've already told you hypothesis is about population. But when you say here, your null hypothesis says the average math scores of 2 classes of 5th graders, you are actually talking about your samples. So this is not correct. Again, hypothesis can only be about population. So what is the correct way for stating your null hypothesis for this research example? And then let me show you here. So the correct null hypothesis will be there is no difference in the average math scores between 5th graders taught with traditional methods and those taught with game-based method. Now, this is the correct version for your null hypothesis. Why? It's clear because now you make your null hypothesis about population. So sometimes you can state your null hypothesis in a statement format, and you can also express your null hypothesis in a mathematical format. You can say H0. H0 means 0 means null, null, and H means the uppercase H means hypothesis. So your null hypothesis is mu1 equals to mu2. What is mu1? Mu1 represents the population mean for your population 1. That is the 5th graders taught with traditional method. Mu2 is the mean for your population 2, which is the 5th graders taught with game-based method. Now you have your null hypothesis of there is no difference. Let's take a look at your alternative hypothesis. So if you understand what is a null hypothesis, it will be easy for you to understand what is your alternative hypothesis. If a null hypothesis is there is no something, and your alternative hypothesis will be there is something. In some textbook, they instead of using alternative hypothesis, they use research hypothesis, and this is the term used in our textbook. But no matter they use alternative hypothesis or they use research hypothesis, you know it means the opposite of your null hypothesis. There is something. Okay? Now let's take a look at the alternative hypothesis for the research example we used before. You can still remember your null hypothesis says there's no difference in the average math scores for 5th graders taught with traditional methods and 5th graders taught with game-based method. Now your alternative hypothesis will say there is a difference. Or you can state a little bit different, say the average math scores of 5th graders taught with traditional methods is different from the average math scores of those taught with game-based method. So it's obvious that alternative hypothesis says that there is a difference. Okay? So again, you can also express your alternative hypothesis in a mathematical formula. You can A here represents alternative hypothesis, and uppercase H means hypothesis. So your your alternative hypothesis is mu1. You understand mu1 is the mean for population 1, and then your mu1 is different from mu2, means mu1 does not equals to mu2. And this is your alternative hypothesis in a mathematical formula format. If you state your alternative hypothesis as there is a difference between mu1 and mu2, you are not indicating which one is larger and which one is smaller. But you can definitely state your alternative hypothesis differently by indicating the direction of the difference or the relationship. I will show you what I mean here. So you can state your alternative hypothesis by seeing the average math score of fifth graders taught with traditional method is greater or smaller than the average math scores of those taught with game-based method. So that means what you're indicating a specific direction of the difference. So your alternative hypothesis in mathematical formula will be mu1 larger than mu2 or mu1 smaller than mu2. If in your alternative hypothesis you are not indicating the specific direction of the difference or the relationship, we call this type of alternative hypothesis non-directional or two-sided hypothesis. But if you indicate a specific direction of the difference or the relationship, and then we call this type of alternative hypothesis as directional or one-sided hypothesis. Now you're done with stating your hypothesis. So, and then the next step for hypothesis testing is set alpha level. But now I will skip this step and go directly to step 3 and 4. And when I'm done with step 3 and 4, I will come back. Now we have skipped step 2 and we are now at step 3. So step 3 for hypothesis testing is to calculate test statistics based on the data you collected from your sample or your samples. We are using the same research example we used before, and then you have your null hypothesis. There is no difference in the average math score between fifth graders taught with traditional method and those taught with game-based method. And then what you will do at this step is you are going to calculate your test statistics to test your null hypothesis. If you finish other PowerPoints and videos I created for this week, you should be able to know that what we are actually doing here is we are doing an independent samples t-test. And then the test statistic we are calculating is the t-test statistics. And then this is the mathematical formula for calculating t-test statistics. Please don't freak out. I will not ask you to use this mathematical formula to calculate t-test statistic for this class by hand. You can, but I definitely will ask you to ask SPSS to calculate the t-test statistics for you, but not by hand. So, but I do want to show you this mathematical formula because I want to show you something which I believe is missing in a lot of other statistic classes. Now let's take a closer look at the mathematical formula for calculating t-test statistic. Let's look at it here. So we have x1 bar, x2 bar. So you know x1 bar is the mean for your sample 1. And x2 bar is the sample mean for your sample 2. You have already collected your data from sample 1 and sample 2, and you can easily calculate the mean for sample 1 and the mean for sample 2. So in other words, these two numbers are known because you have already collected your data from your samples. And let's look at the denominator. So N1 is the sample size for your sample 1. N2 is the sample size for your sample 2. what is S1 squared or S1? S1 is the standard deviation for sample 1. You have already collected your data. You can definitely calculate the standard deviation for your sample 1. Similarly, you've already collected your data from your sample. It will be easy for you to calculate the standard deviation S2, which is the standard deviation for your sample 2. You can easily calculate the standard deviation for your sample 2. In other words, all these numbers, N1, N2, S1, S2, all these numbers are known. They can be calculated from the data you collected from your samples. So all these numbers are known for the denominator. For the numerator, you know x1 bar and you know x2 bar, which can be calculated from your data. But do we know mu1 and mu2? As we mentioned earlier, that we have no knowledge about our population. Those parameters for populations are unknown. Okay, so if we don't know mu1 and mu2, and then there's no way we can calculate the t-test statistics. We can calculate t-test statistic unless we know these two numbers. With mu1 and mu2 unknown, we will not be able to know the value of mu1 minus mu2. But we need to figure out a way to calculate our t-test statistics. How? And then here is how statisticians go about doing this. We can get rid of mu1 minus mu2 by assuming null hypothesis is true. You will ask me, what do you mean? Why we wanted to assume null hypothesis is true? Think about this. If you look at this formula here, if we assume null hypothesis is true, means mu1 equals to mu2. And then if mu1 equals to mu2, mu1 minus mu2 equals to 0. Again, if we assume null hypothesis is true, that means mu1 minus mu2 equals to 0. With this number here being 0, and with all other numbers in this formula known, based on our data collected from the samples, we will be able to calculate our t-test statistics. With mu1 minus mu2 equals to 0, and then now we have a new formula to calculate our t-test statistics. I believe in many textbooks showing the mathematical formula for calculating t-test statistics, they only show us this formula, leaving this formula out. But for me, this formula is really important because with this formula, you can understand how we are connecting data collected from our samples with the population parameters. And you should be able to, by looking at this formula and by knowing we assume null hypothesis is true, so we can get rid of mu1 minus mu2. If you know this, and you will be able to know better how we actually calculated our t-test statistics. And then you should be able to have a better understanding about inferential statistics. Now, let me go to my next slide about step 3. We have already calculated t-test statistics by assuming null hypothesis is true. And then I hope you can still recall that when I talk about z-scores last week, we talked about z-score and the corresponding area underneath the normal distribution. what I have here in these two graphs are t distribution. Okay, t distribution shape-wise is very similar to normal distribution or normal curve. So if you understand the z-scores and corresponding area underneath the curve, you will be able to understand this. If I have a t-test statistic, and a t-test statistic is, you can understand it as a z-score. If we have a z-score here, we will be able to find a corresponding area underneath the curve. And in this area, we call it a p-value. Okay? So if you look at this graph, I have this area plus this area as my p-value. You will ask me why for this graph, we only have this area as my p-value. As for this one, I have two areas together as my p-value. My answer for this is, if you have only a p-value on one side, that means you are doing a directional hypothesis. You are testing a directional hypothesis. Still recall? I believe I mentioned this earlier about the difference between directional and non-directional. And then you can, if you go back to that slide, you will be able to see that when I talk about directional hypothesis, I also use the term one-sided. So this graph shows you the directional hypothesis is also has the name, say, one-sided. So you can see from this graph that one side means what? I only have one area on one side represent my p-value. But this graph shows non-directional. As I mentioned before, non-directional hypothesis is also called two-sided. Why two-sided? As you can see in this graph, I have two areas, one on this side, one on the other side. So I have these two areas together represents my p-value, and this is why we also call non-directional hypothesis two-sided hypothesis. If you understand the z-scores and the corresponding areas underneath the normal curve, you will be understand here with any t statistic you calculated from your sample or your samples, you will be able to find a corresponding area. We call this area p-value. Because our t statistic is calculated by assuming the null hypothesis is true, and then we can also say we obtain our p-value by assuming the null hypothesis is true. Now let's take a look what p-value means. If you look at the p-value here, it lies to the right-hand side of your t statistic. That means p-value is the probability of finding a t-score equal or larger than the calculated t statistic, assuming the null hypothesis is true. So larger p-value, higher probability. Smaller p-value, lower probability. Now let's take a look. When p-value is very small, what does it mean? Okay, so when p-value is very small, that means when this area is very small, it suggests that it's very unlikely to obtain the observed or calculated t-score, or to obtain a t-score larger than the one you calculated. But the fact is, you have already observed or calculated this t statistic from your data. And then it's a fact that has happened. But the p-value is telling you it's unlikely to get such a value or such a t-score. So you might have already noticed that the p-value here is contradicting with the fact that you have obtained such a t-score from your data. And then now the question is, what's the problem here? The problem is with your assumption that the null hypothesis is true. In other words, your assumption that the null hypothesis is true is problematic because the data collected from the sample are not compatible with or do not provide evidence for the assumption that the null hypothesis is true. So, based on the data, the null hypothesis should be rejected. Again, you're going to reject your null hypothesis when the p-value is small. Another question here, how small is small? To answer this question, we have to go back to our hypothesis testing step 2. Step 2 of hypothesis testing is set alpha level. But before we talk about alpha, let's talk about type 1 error and the type 2 error. If you look at the table I have here, okay, if you look here, if you know H0 means null hypothesis. So if the truth is the null hypothesis is true, what will be your correct decision? Are you going to reject it or retain it? Okay, yes. If your null hypothesis is true, the correct decision is to fail to reject it. We don't use retain. Instead, we use to fail to reject. So hope you can get used to it. Okay, so when null hypothesis is true, the correct decision is to fail to reject the null. What about if the truth is the null hypothesis is false? And then the correct decision for you to do is you reject your null hypothesis. But let's look at these two. What about if the truth is the null hypothesis is true, but you reject it when it is true? You made a mistake. And then we call this mistake type 1 error. Let's look at this. When your null hypothesis is false, you fail to reject it. You also made a mistake, and this mistake is called type 2 error. Okay, as you can see, I put it here. We also call type 1 error false positive, and then we call type 2 error false negative. Now you understand what is type 1 error, and now let's take a look at what is alpha. Alpha is the rate or probability of type 1 error. Conventionally, alpha level is set between 0.01 and 0.05. These two numbers respectively indicating 1% and 5% chance you will reject a null hypothesis when the null hypothesis is true. In other words, they indicate 1% or 5% chance you will make type 1 error. You should be able to find a lot of research studies setting their alpha level at 0.05 and some other research studies setting their alpha level at 0.01. You might ask me when I should set my alpha level at 0.05 and when I should set my alpha level at 0.01. So I hope you can understand reducing the alpha level from 0.05 to 0.01, you reduce the chance of making type 1 error. But at the same time, it will be harder for you to detect the difference or the relationship you are interested in. So the rule of thumb is if you are doing an exploratory research study, you probably wanted to detect a difference or a relationship, and then you would like to set your alpha level a little bit higher at 0.05. But if you are doing a research study that is confirmatory in nature, meaning you are doing a study a lot of people did before, and then you probably wanted to set your alpha level at lower level at 0.01. One more thing I want to talk about alpha level is a specific alpha level corresponds to a specific critical value and on a distribution curve. This may sound difficult to understand, so this is why I'm going to show you three graphs. Please look at those blue shaded areas here. I have on these three graphs, and also look at these numbers here. So my question is, do these numbers and shaded areas ring a bell about anything we talked about before? I hope your answer is these blue areas and these numbers here reminded you of test statistic and p-value. As you can recall, each p-value is an area underneath the curve, and each p-value will have a corresponding test statistic, which looks like the value here. And then I would like you to know here in what I have on these three graphs, these blue shaded area is our alpha. Okay, and then each of these blue shaded area, which is alpha, they will have a corresponding critical value. So again, it's exactly like a p-value has a corresponding test statistic. Our alpha will have a corresponding critical value. We also call this shaded blue area our alpha area. We also call it the rejection region. And then I will talk about why we also call it alpha, this shaded area here, rejection region later. I have two graphs on this slide. If you look at this area here, this is my alpha. And now my alpha is set at 0.05. And my alpha area here has a corresponding critical value, which is here. If you look at my second graph, this area here is my p-value. And this p-value area has a corresponding t-score or t-test statistic. Now let's go back to the question, how small is small for our p-value? The answer is, when p-value is smaller than alpha, we will say p-value is small enough, and then we can reject the null hypothesis. Why p-value smaller than alpha, we say it's small enough? If you can recall, alpha is a possibility for us to make type 1 error. If we say p-value is less than alpha, we are seeing p-value is even smaller than the chance that we can make a type 1 error. So in that case, we say p-value is small enough and we can reject our null hypothesis. Now let's go look at these two graphs again. As shown in these two graphs, you can see my p-value here, represented by this area, is smaller than this area, right? Because this is my alpha. So you can see actually p-value represented by this area is smaller than alpha, which is represented by this area. As we mentioned before, our p-value always has a corresponding t-test statistic. And then our alpha has corresponding critical value. And I hope you understand this line here represents our x-axis. In other words, values increase towards this direction. That the same thing for this line here represent my x-axis. Values increase towards this direction. So if you compare the critical value and the t-test statistic, you will see, okay, actually, when p-value here, this area, is smaller than alpha, it also means your test statistic is larger than your critical value. Now, if you understand what I have here, you will understand because my p-value, this area is smaller than alpha. So if we lay this graph on top of this graph, you should be able to see my p-value area is actually within this alpha area. Because when p-value is smaller than alpha, and we reject the null hypothesis, if we lay this graph on top of this one, p-value smaller than alpha means p-value will be within this alpha. And then we are going to reject the null hypothesis. So this is why we sometimes call this alpha area also called rejection region. Meaning, if your p-value is smaller than alpha or your p-value is within this area, you're going to reject your null hypothesis. This is why we call alpha region or alpha area, we also call it rejection region. Now we have finished talking about the first 3 steps of hypothesis testing. As a review, of the first step is state null hypothesis. Step 2 is set alpha level. And the third step is calculate test statistic. Now we come to step 4. Make a decision about rejecting or retaining the null hypothesis. If I ask you when you can reject your null hypothesis, your answer will be when the p-value is less than the alpha level, you're going to reject the null. If I ask you when will you fail to reject the null, and your answer will be when the p-value is greater than the alpha level, you're going to fail to reject the null. Based on what I talked about in the previous slide, you should be able to understand p-value is less than alpha level is the same thing as the calculated test statistic is higher than the critical value. And p-value is greater than the alpha level is the same thing as the calculated test statistic is lower than the critical value. Okay, so this is your decision about either rejecting the null hypothesis or fail to reject the null hypothesis. This is my last slide on the topic of inferential statistics and hypothesis testing. For this slide, I would like to talk a little bit about what is statistically significant. We know that when p-value is less than alpha, we're going to reject our null hypothesis. And we can conclude that the result is statistically significant. But what does it mean when we say the result is statistically significant? I hope you can still recall our null hypothesis states that there is no difference. There is no relationship. I also hope that you can still recall null hypothesis is about population. So when we reject the null hypothesis, that means there is difference or there is a relationship in our population. So when we say the result is statistically significant, we mean there is a difference or there is a relationship in the population. So today we talked about statistical significance, we talked about the 4 steps for hypothesis testing. We also talked about what is inferential statistics. These are all I want to cover today. If you have any questions, please don't hesitate to email me. Thanks.